likely to be in an atom. So we've got the electromagnetic spectrum here. And there's a lot on this slide, and not all needs to be written down. So if we're looking at the electromagnetic spectrum, that's one thing that we'll need to write down. And knowing that this scale goes from radio waves to microwaves to infrared waves to visible to UV light to X-ray and to gamma rays would be good to know. And when dealing with the visible spectrum, we can look here. We see that the red light is near where we have infrared, and UV light, ultraviolet, is on the side that we have our purples or violets. So we can see kind of where this rainbow comes into our electromagnetic spectrum. So we have a lot of different waves out there, but the only ones that we actually see are what's in the visible range. Some animals and insects can see things in the UV and infrared ranges, but visible is all that we are able to sense. Let's take a look at a couple of definitions. So one definition for us is wavelength. That is how that last slide, that electromagnetic spectrum that we were looking at, was organized. So the wavelength is the distance between peaks. So if we've got our waves there, and I pick two peaks, that distance between there and there is my wavelength, which we often denote with the Greek symbol lambda, meaning wavelength. Another word for us is frequency. And that we relate to the number of peaks that pass a position in a given time. With those definitions, let's look back at our last slide. So looking here, we see that the radio waves are the longest wavelength, or longest lambda, longest wavelength, which means that it is going to have the shortest frequency. I just misspoke there. Longest lambda means that it's going to take more time for waves to pass through, so it is the lowest frequency. On our other end, at our gamma rays, which are about the size, if we're looking at the wavelengths are about the size of an atom. The wavelengths on the radio waves are about the size of a really tall building. The gamma rays have the shortest wavelength, or lambda, shortest wavelength, and the highest frequency. At this point, that is what I need you to know about the electromagnetic spectrum. So we know a lot about electrons due to the emission spectrum that we are able to see or that we are able to sense in other ways. And what the emission spectrum is, or is due to, is electrons that are absorbing energy. When they do that, they go to a higher energy level, but that's unstable for them, so they're always going to return to their original energy level. And when they do that, they lose energy in the form of light, or a photon, a packet of light energy. Energy levels around the nucleus are all fixed, so the wavelengths that these electrons can release those photons in are fixed as well. So let's diagram this out a little bit. Let's say, and let's see if we can find some I was hoping for some shapes easily. Let's see. I want a circle. So, let's say we have a hydrogen atom, and that's my nucleus in the center. Hydrogen has just one proton in the nucleus, so that's my proton. And around I've got my first energy level, my second energy level, my third energy level, oops, and my fourth energy level. Now these are not to scale, and they are not what we actually see. This makes it seem like we've got the sun in the center and the planets rotating around in a common way. Atoms don't work that way. The electrons don't move in a fixed orbit like the planets do. So please don't get that misinterpretation. I've got my hydrogen, one proton in the middle, no neutrons in most atoms of hydrogen, and it's going to have one electron. So let's draw out an electron in my first energy level, because that's where it's going to be most stable, close to the nucleus but not too close. It's going to be somewhere in a spherical area around the nucleus at a specific distance away. Well, if I have some energy that comes into my system and interacts with my electron is going to move to a higher energy level. Let's say it goes all the way out here. So I'm not in the first energy level anymore, I'm in the fourth energy level. Well, eventually, my electron's gotta come back to where it was before. So it's gonna go back to that original spot. Sometimes it'll make some stops in between. It'll go to the third energy level, then the 2, maybe it'll go to the 2 and then to the 1. There's all sorts of different things that can happen with it. What it's going to do as it does that is release energy in the form of a photon. Okay, it's going to release some light in a way that we're able to see. We're going to be doing that in lab next week, exciting some electrons and then seeing what happens as a result. We can see, oops. Oh. Perhaps not. Energy levels, I wasn't able to get it totally drawn on there, but energy levels are not evenly spaced. The higher the energy level, so the further away from the nucleus, the smaller the difference is between energy levels. So they get closer together the further out we go. The higher energy level is the further out. And then eventually they begin to converge, so they get closer and closer together, and then until the point where you can't tell any difference. And this is where and we would be able to form an ion. An electron would leave, and that's how much energy would be required to make that electron leave. And then it becomes an ion, specifically a cation, because it has lost an electron. Hydrogen is our easiest of the atoms to study because it does only have one electron. And what we see here is after an electron has become excited, so it's gotten some energy from out externally, and it starts going back to different levels. So here we see that it goes all the way out to the 7th energy level and starts dropping to the 3rd energy level. Well, when it does that, we can see an IR spectrum. We've got a wavelength in the infrared, so we would need a special device to see that. If we have an electron that's excited all the way to the 6th energy level and drops down to the 2, does not drop down exactly to the 1, then we're going to see energy in the visible spectrum in kind of a violet-y color. As we go down, we can see here that if we're going from the 3rd to the 2nd energy levels, we're seeing a red image that we're able to detect in the visible spectrum. If we're going down, back to the original ground state from any of these energy levels, then we're going to be seeing, we're able to sense UV energy. As we add more electrons, these atoms become much more difficult to study, and much more calculus goes into that as well. So if we look at a periodic table, we're going to be able to determine what an electron configuration is for a specific element. And the electron configuration is basically the roadmap to where the electrons are. Notice a few things on this periodic table before we move on to describing what the different things mean. I've got some big numbers, 1 through 7, 2 through 6, 3 through 6, 4 and 5, and I've got some letters, S, P's, D's, and F's. At this point, they're colored just for your ease of seeing the differences, but nothing more than that at this point. So now that we've seen some of those differences, let's talk about what these different things mean. The numbers we said we saw between 1 and 7, those are the energy levels. From here on out, I'll do EL for energy levels. Those energy levels are the distance from the nucleus. One being the closest, 7 being the furthest. Okay, we also saw things like S, P, D's, and F's. These are keys to us as to the shape of the probability of where we will find the electron. The S shape is spherical. These are all in 3 dimensions, so they're hard to view on here. The S is spherical, and it can hold 2 electrons. And if we look back at that image, we saw that each of these have 2 boxes. So the 7th energy level S has 2 boxes, 6th energy level S has 2 boxes, 5, 4, 3, 2, and here we notice an odd thing, that helium is an S as well, even though it's colored funny here. It goes over there because it's also an S. So we can see each of the S's has 2 boxes. That means that we can hold 2 electrons. So 2 boxes are the same as 2 electrons. P is another shape. It's kind of like a figure 8 or an infinity symbol. And it could go in the x-axis or the y-axis or the z-axis coming out at us. And it's basically like taking 2 balloons and tying them together at the knots. Each of them can hold 2 electrons. And since we've got them in 3 different directions, that means we have a total of 6 electrons maximum. So let's see if our theory that we just worked with works for us here as well. So if we have the 2p energy level, count how many boxes I have. I have 1, 2, 3, 4, 5, 6. I do have 6 with each of them. So the p's can hold up to 6 electrons because we're adding an electron for each of these elements. As we add 1 proton, we add 1 electron. And so we fill up that with 6 electrons. The d's are kind of odd. They look like a clover leaf. And again, they could go in 3 dimensions, plus a couple of funny things, and they hold 10 max. And then the F is not something that you're going to need to know the shape of. I'm just going to call it funky here. It's an oddball one, and they can hold up to 14. Okay, with those things in mind, we may now start looking at what an electron configuration could be. So let's start out with one and decode it before we start making our own. So let's say I have an element, I'm not telling you which one yet, that has 2 electrons in the S shape in the first energy level. That's how this all breaks down. So this big 1 and this big 2 are the energy levels. The S's stand for the shape. And then the top number, the superscript, are the number of boxes or electrons that we have. So we can see a couple things out of this right away. We can see if I add my electrons, that my total number of electrons is equal to 3. Now if I look at my periodic table, my third element that has 3 electrons in it is lithium. And this happens to be the roadmap that tells me where my electrons would be around a lithium atom. So let's try a few. Let's start out really simple. And before we do, let's remember that the helium and the hydrogen are both over here in the 1s energy level. 1s, 2s, 3s, 4s, and you will never be asked in IB anything above calcium. Then we have 2p and 3p, and that's all we're going to have to worry about. So let's take a look at hydrogen. Let's start there. So I see that hydrogen is right here. So I have the first energy level with the S shape, and there's just one box to get to hydrogen, or 1 electron. So 1s1. My 1 electron in hydrogen is in the first energy level in a spherical shape around the nucleus. Now let's take a look at helium, one of my noble gases. I have 1s again, first energy level, S shape, and I have both boxes. My helium's here this time. So I have 1s2. Lithium, we looked at a little bit already. I start out my same way. I always start at the top. I have 1s2 because I filled in both of those. Then I go down to my next level, 2s1. Notice that we are reading this like a book, so we are going left to right, and we are going top to bottom. Just reading it like a book. If you are asked for valence electrons, these are the electrons in the outermost level. EL energy level. So, if I'm looking at lithium, I can see that my outermost energy level is the 2, so I'm looking only at this stuff, and there are just one valence electron in lithium. So one valence electron, 3 electrons total, but one of those is in the outermost level and can be used in reactions. The most difficult one that you will have is calcium, so let's take a look at that. We start at the beginning, 1s2 boxes, so 1s2, then down, 2s2. Then we go across to the 2p's, and I have all 6 of them, so 2p6. Then I go down, I'm at sodium now, it's 3s2. And across, 3p6. And then down to 4s2. And I'm complete now. I'm at calcium with my 4s2. I have 2, 4, 10, 12, 18, 20 electrons total. And I look just at my outermost energy level, which here is 4. I don't have any other 4 energy levels with calcium. So I just look at my valence electron is 2. Since it is a metal, it will lose these 2 valence electrons if it becomes an ion. And then it would have the configuration 1s2, 2s2, 2p6, 3s2, 3p6, which is just like argon, which is the goal of all of our elements that become ions. They want to have the same electron configuration as one of the noble gases. And it's going to do it in whatever way is quickest to do it. So if we're in the nonmetals, they're closest to the next nearest noble gas, as opposed to losing a whole bunch of electrons to be like the one prior. But if we're looking at a metal, they are going to more easily lose the electrons, the 1, 2, or 3 electrons, to become like the one before, than gaining all of the ones they would need to get to the one after.